I guess I'm just going to put the diagram up here. Okay, so we got 10 kilometers at 8.5 degrees south of west. Okay, both of them are actually south of west, so we'll start out with the 10 kilometer vector. Eight and a half degrees is a pretty narrow triangle, so something like that. Okay, so your diagram should look something like that. All right, so our next step here is we got to find all the x's and y's. Okay, so if I want to find red x, it's the adjacent side, red y is the opposite side, and on the green triangle, same thing. X is adjacent, y is opposite, so those are our calculations. Okay, and I forgot to start the calculator. So we have cos of 8.5 times 10, okay, 9.89. Kilometers, and that is west. And the sine of 8.5 times 10, okay, 1.48. South. And then for our green triangle, cos of 30.5 times 7.5, and gives us 6.46 kilometers west. And sine of 30.5 times 7.5. Give us 3.81 kilometers south. Okay, so now that I have those, what do I do with them? What's my next step? Yeah, add the x's together, add the y's together to get my resultants x and y. All right, so resultant or purple x, they're both west, so I can actually add them, 9.89 plus 6.46. All right, so 16.35 kilometers west, and y, they're both south, so I can actually add them again. All right, so that'll be our 1.47 and our 3.81. Okay, which gives us 5.28. And that's south. Okay, so now that I know the two sides of that triangle, I can get my overall displacement with Pythagorean theorem. Okay, so that'll be 16.35 squared plus 5.28 squared. Remembering to use all of our decimal places, not the rounded values. All right, so 17.19 kilometers, and then I also need to get theta. Okay, for me, x was opposite, y was adjacent, so I'll be 10 to the minus 1 of the 16.35 over the 5.28, which is going to give me the opposite of this angle here. All right, so I get 72 degrees. And we only have two significant digits, so our final answer is that the displacement is 17 kilometers at 72 degrees west of south, or at 18 degrees south of west if you drew the triangle that way instead. And either way is totally fine. Okay, questions on that? Is it ringing a bell? Okay. I'm going to put a boat question up there. We talked about boat questions yesterday. I'm going to put a boat question up, okay, and see if you guys can figure it out on your own this time. Okay, give that one a try. Incidentally, we've had all these questions about boats being rowed directly perpendicular to the current. You should never row a boat directly perpendicular to the current. It is a really bad idea. Why? Yeah, it'll tip. Yeah, you'll get swamped. Okay? You always want to row a little bit diagonal, either upstream or downstream, or yeah, it'll definitely tip you over. Okay, so just so no one got the idea that that's a good idea or a good way to cross a river. So our diagram for this one, okay, we know that the river is 65 meters wide. Okay, so the first thing we want to do is kind of draw a mini diagram of the river here. Okay, and we know that it is 65 meters wide, at least at that point. Okay, we know that the current is going downstream at 3.6 meters per second east. Okay, and that the rowing speed is 1.3 meters per second north. Right, so that means then that our resultant velocity is this line right here. Okay, and obviously velocity is a vector quantity, so we would need its magnitude and its direction. Calculating that's not terribly difficult. We just have to do a Pythagorean theorem calculation. right? So that'd be 1.3 squared plus 3.6 squared. And it gives us 3.83. We only have two significant digits though, so 3.8 meters per second. I need to get the angle, okay? So that'll be opposite over adjacent, so tan to the minus 1 of 3.6 over 1.3. All right, so we are looking at 70 degrees east of north, or 20 degrees north of east. And so there's my resultant velocity. That's the first part. Now they want to know how far downstream it's going to be when it reaches the other bank. So we're looking for that. Okay, I know how fast the boat is going in that direction, but in order to figure out how far it goes, I need to know how long it does that for. Where can I get that from? Do I have a distance that points straight across? Do I have a velocity that points straight across? Can I use those together? I have to use those together. I can't use any other sides. They don't point in this direction. This is how far and that's how fast in the same direction. So I can calculate the time provided I use two items that go in the same direction. So d over v, 65 meters divided by 1.3. No, the negative, I don't know where that came from. Okay, 65 over 1.3. So it'll take 50 seconds. That worked out well. Okay, 50 seconds to get across. Is that also how long I'll be going downstream in the boat? Well, once I get across, I hit the other bank, I stop, right? I'm no longer going across or downstream. So yes, the 50 seconds is shared by both across and downstream. And that's the thing I have to remember about boat questions, is that both of those velocities share the time. Okay, so the distance downstream is v times t, which will be 3.6 times 50 seconds. Times 3.6. All right, 180 meters downstream. That's how far we end up. Okay, just so you know, that is an incredibly typical boat question. Last year on the unit exam, I had a question pretty much the same as that, except it wasn't the boat, it was the St. Lawrence River, which is much wider. Okay, like it's kilometers across as opposed to meters, but same idea. I wanted the resultant velocity, and I wanted how far downstream they would be after it got across. Okay. All right, questions on the boat questions? Okay, that was one of the two kinds of boat questions. What kind? Was that rowing across or going across? That was rowing across. Okay, I'm going to put a going across question up here. Okay, let's see how you do with that one. Okay, try that one. Okay, so the ferry wants to end up going straight across the river. Okay, so that means that our resultant looks like that. Okay, the river is flowing east at 6.5 meters per second. So that would look like this. Actually, it'll look like this. Okay, if the boat can only go 4 meters per second, okay, what heading must it use? Okay, so, oh, that's not going to work. Why did I make that one so big? That wasn't very smart. Okay, that ends up having to be the hypotenuse. I messed that one up badly, guys. Well, so here's my 4 meter line. It's not supposed to be the longest line, but it ended up being the longest line because I didn't think about it when I made the question. Okay, so hang on, let me think about that one. Yeah, no, it's not you. It's totally, that sounds awful. It's not you, it's me. It's totally me. Yeah, totally me on this one. Okay. Okay, we're just going to walk through this one as an example because I messed it up so badly. Okay? Okay, so we'll change that river current to smaller because obviously it has to be the boat's velocity has to be the hypotenuse and has to be the bigger side here. Okay, so we will have the river going at 3.5 meters per second. We'll have the resultant still end up being straight across the river. Okay, and then we'll have the boat be this side here at 4 meters per second. Okay, so all we're looking for is that angle there. We have the hypotenuse and we have the current speed. Okay, so theta will simply be the inverse sine of opposite over hypotenuse. Okay, and that'll give us our heading. So sine of 3.5 divided by 4. All right, so they're going to have to head at 61 degrees west of north in order to make that one happen. Okay, everybody all right with that? I can't remember ever having put a going across question on the unit exam. And I fear change. So, spoiler alert there. All right. No, we've already done that one. Okay, there are a couple of questions here that I want you guys to try from the workbook. Okay, just going to bring those ones up here. Okay, I want you guys to try 13 to finish off here. because I'm just going to put the diagram up here. Okay, so we got east and north first, and it's the shorter of the two. Okay, that's what your diagram should look like, guys.